Hello everyone, let's talk about some basic Python data structures. Here's an overview of lists, tuples, sets, dictionaries, and strings. I presented this at a conference last year where I led a workshop differentiating between Java data structures and Python data structures. And I think this is a good cheat sheet for you if you're trying to interpret someone else's code or trying to build your own code. Syntax is important, and we see then that the square brackets are used to indicate a list. The parens are used to indicate a tuple. The curly braces are used for sets and dictionaries. The dictionary differentiates from the set by the presence of the colon between the key and the value pair. And a string is just simply a double quoted series of characters. When you're using any programming language and you want to manage data, your consideration is always, what do I want to do with that data? So if I need a list, then I keep in mind that it can be heterogeneous and there can be duplicates. And then I think about what I can do to it. I can add elements to a list or remove elements from the list. If I create a tuple, then I can do some of the things I can do with a list, but I can't edit the tuple after I've created it. If I create a set, I can't have any duplicates. Therefore, if I try to add an element to the set that's already there, it just gets ignored. And those are advantages that you can leverage when you're writing a program to manipulate data. Therefore, a knowledge of the capabilities of the data structures is good, and then the ability to research how to perform the operations on those data structures is very helpful too. So I don't recommend that you memorize. I recommend that you know where to find resources and know how to interpret and apply them. If you can build a search phrase, you can find your answer, and you'll get very experienced in adapting small code snippets into your program. I mean, the smaller the code snippet, the better, and the more narrow the search phrase, the better. Then you'll be able to quickly integrate little pieces of code that you find to solve the problem you're trying to solve. As we get more into the individual data structures, a string is a common data structure across many programming languages. In Python, it's almost completely analogous to a list. You can use the square bracket slicing notation, and you can initialize it instead of square brackets, though, with double quotes. And we'll see more of that as we go along. We think about things that we can do with a data structure or to the data: create, print, append, insert, remove, sort, search, subset, build more complex things, and again, be able to find these things using productive search tools, using useful websites. And as long as you can visualize or conceptualize what you need to do, you can find a way to do it and you're off to the races. Again, here is an overwhelming list of things that a list can do. I'm not going to go through all of these. I don't think it's effective just to bang out function calls one after another. I'll do a few of them to get us introduced to lists and get comfortable with basic list manipulation. I'll go back to Jupyter Lab, our old friend, create a new notebook. Let's start out with just creating a list that's empty. My list equals, and simply by referencing the square brackets, we can get an empty list. To add an element to the list, let's just experiment a little bit before we actually start looking things up. Can I just reference the first index number and attempt to add a value? Well, that doesn't work. I was hoping it would let me add 42 as the first element in that empty list, and that didn't work. Okay. I got a reasonable error message, list assignment index out of range. The index is 0, which would be the first element in the list, and since there is no first element, it won't let me do that. Okay, no problem. I happen to know that I can add an element to the list by calling append, and then I print it out just to get some confidence in what I'm doing. Now the list has 42 in it. I'm on a roll now. How about let's add another element, 43, whoops, 54, and print it out again. You know it's a list because it's delimited with square brackets and the elements are separated by commas. So over time you will intuitively just read that as a list. Can I create another list? Let's just experiment a little bit together. Can I create another list? New list. And can I put elements into the list instead of just using empty square brackets? ABC. I'll tell you what, this is getting a little crowded. Let's take this new list code. Whoops. Let's cut that out of here and let's put it into another cell just to break things up a bit. So now I'm starting with a new variable, new list. I'm using the square bracket notation, and I know that what's on the right side of this assignment statement is a list because it's square brackets separated by commas. And then I'll print that out. Does that work? Okay, that doesn't work. I'd like to have a list with the letters A, B, and C in it. However, I made a syntax error because I needed to put quotes around these things. Otherwise, Python interprets them as variable names or symbol names. By putting the double quotes around the individual elements, still separated by commas, now I have a list of ABC. Remember, in Python, single quotes are the same as double quotes. I have, by habit, been using double quotes. Python often converts them to single quotes. That's perfectly fine. And now in the next cell, what happens if I try to add those two lists together? Is that possible to do? My list plus new list. Does that make sense? Does the plus operator make sense with two lists? The add operation then appears to create a new list by appending the elements from one list to the elements of the other list. We end up with 5 elements in our new list. We can see what the plus sign does. Well, if plus sign works, does the minus sign work? This is getting interesting now. Can I subtract one list from another? No, I can't. Unsupported operand minus for list and list. There's my error message. What I'm trying to do there is not possible. And I don't like to delete things, so I will just put a comment here. This does not run. and I will delete this output. So I can skip this cell. It still exists. It's part of my notebook, but it doesn't work. And if I want to come back to it later and research why I can't do a subtraction or try to find an equivalent way to do what I think I need to do, I can refer to that cell later. This is one of the beauty things about Jupyter Lab, about these notebooks, is that I can run the cells individually, and even if a particular cell is broken, I can skip it and continue on. If I were to hit the double arrow and relaunch the entire kernel, that would traverse through the cells from top to bottom, and it would eventually hit that cell that's broken. But I don't plan to do that, therefore I will just leave it in there. Can I convert a list to something else? Well, we know there are things called sets, right? Convert a list to a set. I have a list already. I have a list called alpha. It's got 5 things in it. I can still use it. And let's say that I don't know how to do that. I don't know how to convert a list to a set. I've reached an impasse. Let's go to our search engine. Python convert list to set. The first result says it will give us 4 ways to do it. And the synopsis of that website says the simplest way to convert list to set is by using the set function. How about that? I'm not even going to click on this. So I'm going to say my set equals set paren alpha, which remember is a list. If you're confused and you're lost and you're just overwhelmed by the amount of code, you can play catch up a little bit, which I do all the time. Print type alpha. You know what? That shouldn't go there. That should go up here. No, it shouldn't, because that doesn't run. So I guess I'll put it in there, sure. Let's see what happens. Not much right now. I'm going to print the type of alpha, which we hope is a list. And then I'm going to create a brand new set from that list. But let's add one more print statement. Print my set. Let's see what we get. There we go. A set is delimited by curly braces with elements separated by commas. And there's our set. Notice the set got reordered. Notice that the original list was 42, 43, A, B, C, and the set is now A, 42, 43, C, B. So we're not guaranteed preservation of order when converting from a list to a set. As we saw in the code, a list can have heterogeneous contents. In this example, I create a list with a numeric integer, a string, which is the character 2, followed by a floating point number 3.3, and that's perfectly fine. Let's play around with this a tiny bit. New code cell in Jupyter Lab, and let's say beta equals, we'll reproduce what was on the slide, 1, a 2, and a 3.3. So 1, comma, quote, 2, quote, comma, 3.3. There is my list. And then I'd like to know 2 things. Of course, this hopefully you already recognize will be the type of beta, which is a list, but I also like to know the type of each element in the list. So let's introduce a way to iterate over the elements in the list. And that's going to be as simple as for E in beta colon, it looks like a for loop, and then I will simply print the type of E. I'm demonstrating that I can access the elements in the list individually and perform some operation on each element. The E that I chose is completely arbitrary. I needed a placeholder for each element as it goes through that loop, one element at a time, and I just decided I would call that E. And that will be beta prints out as a type list. The individual elements in beta print out, as you might expect, as int, then string, then float. Now I could also add E to this print statement. Now I'm printing out the array, the list element itself, followed by the type of that element. List slicing is really amazing. One of those things that you don't see in many other mainstream languages, and once you start to use it, it becomes invaluable. And let's cobble up another list. In this case, I'm just going to go 1 through 5. So I'm going to say my list equals 1, 2, 3, 4, 5. Back to Jupyter Lab, brand new cell. There's my list. And let's say for the sake of argument that I want the last element in the list. I want the 5. And let's say also for the sake of argument there's a lot of complex code. In the meantime, I'm doing things to the list. I don't know how long it is. I've appended, I've deleted, I've merged, I've added. But it comes time for me to extract the last element in the list. Well, that's easy. Last equals my list minus 1. Completely counterintuitive. Why would you use a -1 as an index into a data structure? Python takes that to mean start at the end of the data structure and work backwards. Therefore, -1 is the last element in the list. I could print that out. And I get 5. As you might imagine, print my list -2 will print the 4 in that list. And we get the 4. What about intentionally trying to break this? Print my list bracket -10. There is no element that is 10 backwards from the end. There's only 5 elements in the list. That is destined to fail because we are out of bounds. There we go. Index error, list index out of range. It gives us the line number in which the error occurred, and then you can take steps to fix it. In my case, I will just comment it out because I know it won't run. And let's do another slice. What if I want the 2 and the 3? I don't want the 1, the 4, or the 5. The list has 5 elements in it. I only want 2 and 3. I can say my list, use a square bracket notation again, and I'm going to say 1:3. Indexing starts at 0. That's just a computer. That makes it easier for the computer to deal with what we're doing without going into too much detail. So the first element in a list or a set is the 0th element. And then The 3 is the last index plus 1. So we want to stop before we get to 3. And let's see what we get. We get 2 and 3. There it is right there. We get element sub 1 and element sub 2, which are the 2 and the 3. Also notice that we're actually getting from this operation another list. So slicing, whoops, got the parens in the wrong place. Oh, I sure do. Got carried away here. Hold on. Let's try that. No, they still don't match. 1:3. Type. I found it. It's right there. Let's try that. There we go. This example demonstrates that when you do that slice operation, the result of that is a new list. In this case, a 2-element list. How about this? Let's do the slice again, but instead of doing a type function on it, let's do a len function, which is length, and that should return 2 because we asked for a 2-element slice, and there's the 2. All right, you should be getting basic familiarity with the syntax and the terminology, and you're learning how to think about these problems. I would encourage you to take a look at the difference between extend and append. We've already demonstrated one of those. We demonstrated append, but make sure that you can differentiate between the two. Does the plus sign do an extend or an append? Cobble up some code in your Jupyter Lab cell and see if you can figure out the difference between the two and why you would use one over the other. Tuples. Remember, this is slide 10. If I go back to slide 2, a tuple can have duplicate elements, but it is not mutable. You cannot change the contents of a tuple once you've created it. Keep that in mind. Go back to slide 10. And I'm creating two tuples, A and B. A has 1, 2, 3, 3 elements. B has 4, 5, 6, 3 elements. Then I'm doing an add operation, a plus sign of A and B, and storing the results in C, printing C. And as you might expect, C is 1, 2, 3, 4, 5, 6, a brand new tuple with 6 elements. And then I'm playing a little trick on you because I told you tuples were not mutable. They cannot be changed. But it looks like I'm doing just that when I add A plus B and store it in C. I'm sorry, let me say that again. I'm adding A plus B and storing it in B. It looks like I'm mutating B, but I'm not. I'm actually creating a brand new tuple, and the reference to that brand new tuple is now stored in B. I threw away the original, and I made a new one, and the new one is the result of A plus B. Let's grab that code. I'm going to take everything off this slide, slide 10, back to Jupyter Lab, brand new cell. Okay. And it does work. There's nothing there that's going to fool you. It's just important that A plus B stored in B creates a brand new B, creates a new tuple, stores the reference to the new tuple in B. We didn't edit B, we blew it away and we stored a new tuple there. Splitting hairs, yes, but it's important to understand the difference between an immutable data structure and the opportunity just to blow it away and create a new one. Now let's break this because we told you that tuples are immutable. So B sub 0 equals 42, 42. There you go. You cannot do what they refer to as item assignment with a tuple. It's logically incorrect because tuples are immutable. If you flip back to the slides again and you go all the way back to slide 2 and you observe the first two rows in the table, lists and tuples have a lot of commonality. They're ordered, they can be heterogeneous, they're indexable. The only difference there is that tuples are not mutable. You can't assign new values. And this matters because it makes the tuple much more efficient computationally. So if you're manipulating millions of data points numerous times a day, then choosing a tuple would make your program run faster than choosing a list. But I will tell you that Python is oriented towards lists, and most of the examples that you see are people using lists until they explicitly have to use a tuple, and I'm in the same boat. So optimizing your code, yes, lean towards the tuple, but the general population, the general Python population is going to use lists when they need a data structure. Back to slide 11. We can create a tuple just like we create a list by using the parens, where the list used the square brackets, remember. But we have to put that extra comma in there even if there's only one element in the tuple. Therefore, the example on the slide, we're actually creating a string even though it's got the parens around it, and it almost looks like a list, or it almost looks like a tuple, but it's not. And I'll take that over to Jupyter Lab and twist that around a little bit. And I can see right away there's a problem here because the font from PowerPoint did not map into the correct quote. In Jupyter Lab, I'm going to have to fix these delimiting quotes. Bear with me, please. Quotes are fixed. I have two examples. In the first one, I am only getting a string. We get a string, not a tuple. In the second example, we get a tuple because of the trailing comma. That is illustrated by the print statements which demonstrate the data types. Also notice that we're reusing this variable. In the beginning of the cell, the variable names is a string, and at the bottom of the cell, that variable names becomes a tuple. Not good programming practice. I do want you to see it though because it is common to do that. What I'd rather see you do is create a new variable here. We're not short of space. We're not going to run out of resources in the programs that we write in this class, and a good programming practice is to create that new variable when you need it. Okay, slide 12. There's an attempt to add something to a tuple. And remember, since it is immutable, what we're really doing is creating a brand new tuple, not blowing away or not editing the original tuple. And in this example, we take what we think is a tuple, but it's really not, and attempt to add it to what we know is a tuple. That gives us an error because you can't concatenate a tuple in a string, or an int, sorry. And then the second example, we realize our error and we create a tuple by adding a trailing comma to that parentheses delimited list, and that lets us get away with it. Okay, here's another function. Remember, we talked quite a bit about modularizing our code. And in this example, we're going to go back and process a list again. And this function is going to look through a list and find the maximum value in the list. And I'll tell you, there's a much easier way to do that. It's built into Python. You don't have to write logic to do this. We're just simply illustrating passing something to a function, processing it, and returning a value. And again, I will let's grab all this code off the slide, copy. Let's go back to Jupyter Lab, open a brand new cell. In my brand new cell, I pasted in all of the code off the slide. Take a close look. You will see that this cell contains a function definition and some standalone code. And what happens when you run this cell is it defines the function and immediately runs the following two lines of code, which in fact call that function. Bada boom. The function computes the max value in the list and returns that number. We accept the return value in the context of the print. We convert that value to a string and we print it out. Now let's see if we can break it. Shouldn't be too hard. Sum tuple equals, and I will make a tuple, 100, 3, 23, 4, 200, 6, -1, just some stream of numbers. It's a tuple because it's enclosed in parens. So be on the lookout for the delimiters. The delimiters will tell you what kind of data you're dealing with. And then let's call the function using the same logic we did before. I need to change the name of the variable to sum tuple. This guy will initialize a tuple, 100, 3, 23, 4, 200, 6, -1. Then call the function to find the max. Now we have a problem because the function thinks it's getting a list, and the reason you know that is because you can see some list notation right here. That's the only way you know, is by looking at how it uses that parameter. If we don't pass it a list, if we pass it something that cannot be implicitly converted to a list by Python, we're going to have a problem. Let's see what problem we have. Oops, we have a typo first. What is sum tuplet? Oh, that's this. I'm so sorry. That is sum list. Boy, I really got type crazy there. Now let's try it. Okay. We got our answer because even though this thing is expecting a list, you can see list notation there, it still can deal with a tuple the same way. It can still index on a tuple just like it indexes on a list. Now that doesn't mean this is going to be bulletproof, wonderful code, because if I come back tomorrow, I may do something to that parameter that I can't do to a tuple, but I can do to a list. So there's still a risk there, but in this case it does work. Let's complete the thought. Let's make a dictionary. We know that will cause it to explode. Let's say some dictionary equals, and I'll just cobble something up here. Let's say A colon 100, comma, B colon 200, comma, X colon 300. There's a 3-element dictionary with 3 key value pairs. Now if I pass that to my find max, whoops, that is some dictionary. Okay, there's my new code. The key value pairs, the keys are strings, the values are integers, and can my function deal with a dictionary? Is it using notation that is common to lists and dictionaries? Nope. There's my error, and the error actually says that when I first try to index into the list, I'm using a 0, and in dictionary notation that has to be a key. There should be a key in that data structure with the value 0, and there isn't because our keys are A, B, and C, and therefore it fails. And if I could just revert back to big picture again, most, okay, you're going to hear me say most a lot, and I'll keep saying it, most modern development languages have the capability of telling you that you did this incorrectly in advance. You don't have to run this in C# or Java or C++ to find out or to learn that there's a problem. That's because of the way the languages are structured and the intended purpose of that language. I'm not saying it's a bad thing. I'm just pointing out that it is something that you would like to know. I would like to know that there's a bug in this code. Actually, the bug is right here. I'd like to know there's a bug. I'm passing the wrong data type to my function. Before I call the function, I'd like to know today, because I might not run this code for a week. I might not go through this code path if it's a very complex program. And it's not a good thing to have an error pop up when it's completely out of context and you don't know how you got there because you've run millions of lines of code. Again, possibly a drawback of Python, possibly me on my soapbox, you decide. Back to slide 14. Sets are created with curly braces. In this example on the slide, you can see that it looks a lot like a dictionary, except there are no colons separating key value pairs. So you can think of these as all keys. If you perceive a set as a dictionary with nothing but keys and no associated values, you can conceptualize it pretty well. And in this example, I'm creating a set. If you look at the data closely, the very first element in the initializer is Apple, and the very last element is also Apple. And since sets do not permit duplicates, nor do dictionaries, it'll just ignore that second Apple. Or it may overwrite the first Apple. It's neither here nor there. And we can manipulate that by printing it out. We can also manipulate it by using that for loop that we saw earlier on a list. So let's grab this code off the slide. Back to Jupyter Lab. Brand new cell. Looks good. Visually verify that there's only one apple in the set. The second apple got ignored, or the first apple got ignored, doesn't matter, I don't even know which. When I print it out using the iteration construct, I iterate over the set with the for loop. I decided to use the word fruit as my placeholder. Each time it goes through the for loop, the variable fruit gets replaced with the next element in the set. Can I add an element to a set? Let's assume that I don't know how. Let's go back and do another search. I know I need a set with another element in it. I realize there's another fruit out there that's not my list, my set, sorry. And I will say Python add element to set. Comes up pretty quickly. Python for Beginners is the first site. I'm not familiar with them. W3 Schools is the second site. That makes me happy. I like them. And it says add set items. That's exactly what I want. I learned that there is an add function. There you go. When I go back to Jupyter Lab, and in my cell, I will say fruit set dot add. What's the name of a fruit? Tomato is a fruit. I will put the print statement back in, and let's see if I got an extra value in my set. There he is. There's tomato. Notice that the set is not ordered. It put tomato in where it was happy putting it in. That's because these values are actually hashed, and the order of them being added to, or the order of them appearing in the printout, are reflective of the hash, not of the individual value that you put in. So we learned how to add an element to a set. There's what we just did. We talked about how sets are unique. We can skip this slide. Some things that you might want to do to a set. Again, I encourage you to build your comfort level with researching these things and implementing them in little bits of code. Sort the set. Check for an element in a set. Does it exist? Add an element, which we did. Remove an element. Things that you would want to do to a data structure on a regular basis. So we're going to close with a more complex example. I have a text file that I provided for you on Canvas in the module. You can go grab that text file. It's called fruits.txt. We're going to read from that file into a data structure and then build that whole thing into a function. Now this is jumping way ahead. We'll do more data input and output later. Let's start with just the code as it is on the slide, and we will morph it into a function. Now, in order to follow along with me, and I hope you are, you'll need to do more than just copy paste this code. You're going to need that fruits.txt file. You can find that on Canvas in the Learning module. I already have it in my folder. I'm just working from my hard drive. And I don't need to do anything. I've already got that file. If I double click on it, it will load, kind of sort of load in Jupyter Lab. So Jupyter Lab does provide some browsing capability for just text files. And this text file has line feeds or line breaks that are not quite compatible with Jupyter Lab, so they don't appear as line breaks. If I can I right click on this file? And I can do open with. Well, probably that's not going to help. But I will, just to be more complete, I will show you that text file in Notepad. Yep, see, it's not that compatible there either. You still got, actually I'm wrong, there are just tabs in there. They aren't new lines, my mistake. So there's a space, and then, I'm sorry, there's a comma and then spaces or tabs between the fruits. My fault. I overreacted there. And the tabs appear as these little funky characters. But we're good. We can still open it and read it. Anyway, let's make a brand new notebook. Paste in all of that code off of the slide. It looks like it's fine. I don't see any problem with the quotes. Looks like the quotes carried over. That's good. Let's talk about briefly what this does. We're opening a file. Okay, make sure that fruits.txt file is in your current directory. Make sure that if you're in a Unix-based OS, make sure that the file name matches precisely the file name in the program. And you can see that I don't have that situation right now. Since I'm in Windows, Windows isn't case sensitive when it comes to file names. So a capital F in a file name is the same as a lowercase f in Windows. If you're doing this on a Mac or Linux, you're going to definitely want to edit this f down to a lowercase f to make the file names match. After we've opened the file, we're going to read one line from the file by calling the readLine function. And then, just to do a little bit of debugging, we'll print it out and you'll see what we read. And then you'll see what data type we got when we called readLine, and that'll be a string. And then we're going to use the split function on the string to break it up by commas, and that will give us individual fruits in individual elements of a data structure. We don't know yet, at least we're not going to say, what the split function returns as far as what kind of data structure. Does it send us a list? Does it send us a tuple? Does it send us a dictionary? We'd have to look up the split function to see what it's doing for us. And then we print that out to monitor our progress. And we then realized that the file had some extra spaces in it. Therefore, some of our fruits have leading and trailing spaces, which is awkward. So we do a for loop, and we access the individual elements in our list. We know it's a list by now. And we strip each element in that list, which removes the leading and trailing spaces. Then we print it out just to get another level of confidence that we're doing things the right way. Finally, we append that stripped fruit with the leading and trailing spaces removed to a new list, and then we print that new list. Okay? When we get to the bottom of all this code, we should have a beautifully formatted list of fruits with no leading and trailing spaces tucked into individual elements of a list data structure. Okay? That's our goal, is to get this thing into a model that we can deal with. And we can often prefer to deal with things one element at a time. There we put everything into a list instead of having one big long string of text. And let's see what happens when we do this. There it is. There's all the intermediate output. And finally, at the very bottom, there's the list that we end up with. We were able to remove the tabs and the leading and trailing spaces and combine the individual fruits into a list. This is a common practice. We're often given dirty data. It came out of a spreadsheet that wasn't managed very well, or it was scraped from a website, and we need to process it. And this is the mindset that we go through. We step by step split it along the commas if possible, take off the leading and trailing spaces, build a brand new list if necessary. And I'll be the first to admit that we could have done all of this in one line of code. There are whiz-bang Python programmers who could do all of this in one line of code. And given enough time, I could probably figure that out myself. But I don't think that benefits us at this point. I think you need to see it in a stepwise fashion. It works. It takes 10 lines of code where someone else might do it in one line of code. I'm not judging you on that. Okay, we're not to the point where we can be so picky as to require something to be done in one line. And I would not judge yourself against those type of highly capable programmers either. But it would be really nice if this was in a function, because then we could call the function over and over and use it in different programs, and it would be more of a modular thing. So let's think about how to break this up into a function. What we would like the function to do, first of course it has to have a name. Let's put the def in there. Def process file. I made up the name, just an arbitrary name, process file. And then of course we realize we have to indent everything. I don't think I can do it this way. Oh, I can. So I can highlight blocks of code and then press the tab key, and that will indent the entire highlighted block. And that's wonderful. At the bottom of this logic, I'm doing a print, okay, which is nice for debugging, but I don't have a return statement. This function wouldn't have a lot of value unless it sends something back to me. I'm going to add a return statement, return fruit list. There's my function. It barely fits on the screen. It's called process file. It doesn't accept any arguments yet. It does a bunch of printing, which I'm going to find to be very annoying. When I start calling it over and over, it's going to clutter up my screen like crazy. I'm going to comment out all these print statements right now because I know I will be doing that later anyway. All the print statements are gone. All it does now, and you can see it's collapsed into a much smaller function. There's basically half of it was print statements. All it does now is open the file, read one line of the file, do a split on commas, and then process the individual elements that were split by removing leading and trailing spaces. The result is a wonderful, clean list data structure that I send back using a return statement. I can run this. I haven't run it yet. There we go. Now it's run. Now I have a function. In the following cell, I can say my fruit equals process file. And as always, I'd like to see some output. I will print my fruit. There's a demonstration of a move towards modularity. My function does all the neat things that only need to be done once. And I can call it as necessary, and I don't have to stop and think, where did I put all that code? Click Run on this second cell. There's my output, and there's my cleaned up list of fruits. That works great. Let's consider it a little more. This function, while it is useful, it still is locked into processing only one file name. Unless my file is called fruits.txt, this function has no value to me. Therefore, it would be better to have the file name passed in as a parameter. So that file name parameter would then become the first argument to the open function call. Watch it, I'm going to cut. Well, you can't see me do it, but I'm going to do a Control X on that. Actually, right there, will that work? No, that cuts the whole cell. I don't want to do that. Control X on the file name and then replace that with a parameter name. Down in the other cell, I will paste in the file name. This increases the flexibility of the function because I can pass it any file name and it will still work. We're just moving towards more modularity, more flexibility. Of course, we have to rerun the cell to define the function, and then we can rerun the cell that calls the function. We get the same results. Everything's good. Flipping back to the slides again, slide 19 here is a summary of what we just did. The only thing that we didn't do was add the doc string. And I will go back and I will take that right off the slide and go back and add the doc string to my function. It goes right inside the first line. There it is. The doc string is a documentation tool for other programmers that might use that function. It defines the parameters, if any, and what they should contain. It also defines what kind of data structure is returned. I shouldn't really say define. I say it explains what they are. All right, we have a nice little modular function. You don't have to run it again necessarily because all you did was add documentation, but you can if you want to. And it still works. And that's the end of this presentation. Please post any questions in the FAQ. Thank you very much.